Hi, hello, welcome back. For today, we will be discussing the continuation for our error detection and correction. Okay, so we ended up with the uh, cyclic codes and polynomials. Okay, so for this video, we will be discussing another type of error detection. Okay, so the next type or technique that we're going to discuss for this video is what we call the checksum. Okay, so a checksum is an error detecting technique that can be applied to a message of any length. Okay, so the checksum technique is mostly used at the network layer. So we've mentioned before that there are different layers in our um, communication systems. Okay, so usually checksum technique is used in the network layer and the transport layer rather than the data link layer. So the previous types of techniques that we have discussed earlier or previously were being used in the data link layer. Okay, so what happens or what is happening in the checksum technique? Okay, so at the source, if you're going to look at the figure, so at the source, the message is divided into m bits. So it says there that it can be applied to any message length. So we will be using m as the generic number of bits in our messages. Okay, so at the source, the message is divided into m bits. Okay, the generator. So we have a generator there, as you can see in the figure. So the generator then creates an extra m bit. Okay, so extra m bit unit called the checksum. Okay, so your m bit must be of the same length with your other messages. Okay, so that extra m bit that was generated by your generator is what we call the checksum. Okay, so that checksum will be sent together with the message. Okay, so the message now includes the actual message plus your generated checksum. So at the destination, so looking at the destination, the checker, so as we can see, we have a checker there. So the checker creates a new checksum from the combination of the message and the sent checksum. Okay, so if the new checksum is all zeros, okay, so if the new checksum is all zeros, the message is then accepted. Okay, otherwise the message is discarded. Okay, so in the real implementation of checksum, the checksum unit is not necessarily added at the end of the message. So as we can see here in our figure, here in our example, the checksum is added at the end of the unit. So in real implementation, it can also be inserted in the middle of the message. So the checksum may be placed anywhere within the message. Okay, so what is the concept behind checksum? Okay, so suppose that the message, suppose we have a message. Okay, so our message is a list of 4-bit numbers, okay, that we want to send to a destination. Okay, so in addition to sending these numbers, we send the sum of the numbers. Okay, so at the receiver side, okay, so the receiver adds the numbers and compares the result with the sum that was sent in by the sender at the sender end. So if the two are the same, so the receiver assumes that there is no error. Okay, so therefore it accepts the numbers and discards the sum. Okay, so the receiver will already remove the checksum or the sum because it is not included in the original message. Okay, but okay, so if the two are not the same, okay, so otherwise there is an error somewhere and the message is not accepted. Okay, so the idea of a traditional checksum is very simple. So from the term, you're checking the sum, okay, of the sent messages. Okay, so for example, we will be showing this using a very simple example. For example, we want to say send a set of numbers. Okay, so for example, we want to send Okay, so for example, we want to send these numbers. So I want to send 7, okay, 11. So we have 12, 0, and 6. So I will be sending 7, 11, 12, 0, and 6. So I have five numbers, okay? So we will not be sending only 7, 11, 12, 0, and 6, but rather, okay, so we will be sending the message together with a checksum. So what will be the checksum? Okay, so we will be sending this message instead. So we will be sending 7, 11, 12, 0, and 6. Okay, plus the additional checksum, which is equivalent to 36. So 36 is included in the sent message. Okay, so where did we get 36? We just simply add 7 plus 11, okay, plus 12 plus 6. So the sum is 36. Therefore, we append the sum in our original message. Okay, so at the receiver end, what the receiver will do is they're going to add again those five numbers. Okay, so if the result is 36, so therefore the receiver will accept the numbers, okay, but it will discard the 36, which is the sum. Okay, so this is how we show a simple example of a traditional checksum. Okay, now, so from this example, okay, so from this previous example, there is one major drawback. Okay, so we said earlier that so if we're going to go back to the earlier problem, suppose we wanted to send a message with 4-bit numbers. Okay, so we have a drawback to this method. Okay, so why? Because all of each numbers, so the 7, 11, 12, and 0, we can represent them all in 4 bits. Okay, so remember the codes. Okay, so as long as the number is below 15, okay, 15 or less, it can be represented in 4 bits. So 7, 11, 12, 0, and 6, they can all be presented in 4-bit numbers. Okay, however, 36, we cannot represent 36 using only 4 bits. Okay, so we cannot represent 36 by using only 4 bits. Okay, so what's the solution then? Okay, so one solution is to use the ones complements arithmetic. Okay, so we will be using the ones complement addition. So how do we do this? We can represent unsigned numbers. Okay, so unsigned numbers between 0 and 2 raised to m. So m is the original number of bits in each messages, using only m bits. Okay, so if the number is more than m bits, the extra leftmost bits need to be added to the m rightmost bits. So we call this wrapping. Okay, so this term is what we call wrapping. So one solution, because since 36 cannot be represented by using only 4 bits, we are going to make use of the ones complement arithmetic. Okay, so in this example, the binary number for 36 is given by 1 0 0 1 0 0. So that is base 2. Okay, so this is 1, 2, 3, 4, 5, 6. This is 6 bits. Okay, so it says there if the number is more than the m bits, so in our example we have 4 bits supposedly, the extra leftmost bits need to be added to the m rightmost bits. Okay, so we have 2 extra leftmost bits. Okay, so to change it to a 4-bit number, we need to add the extra leftmost bit. So what is that? That is 1 0. Okay, so this 2 extra leftmost bits, so that is 1 0 base 2. Okay, plus, so we this is equivalent to the extra or the remaining rightmost bits here. So that is 0 1 0 0. Okay, so in binary. Okay, so adding them together, so you have that will give you 0 0, so that will give you 0. 1 plus 0, that will give you 1 1, so you will just copy 0 and 1 there. So this is the sum of the two leftmost bits and the remaining rightmost bits, so that will give you 0 1 1 0. So in this case, the decimal value for this is 6, okay, to the base 10. So it is already represented in 4 bits, okay? So instead of sending 36 as the sum, we can send 6 as the sum of 7, 11, 12, 0, and 6, okay? So therefore, we have to send the message 7, 11, 12, 0, 6, and then another 6 here. Okay, so the receiver can add the first 5 numbers in one's complement arithmetic. Okay, so if the result is 6, the numbers are accepted. Otherwise, it will be rejected. So this is how you make, okay, so the sum equal to the required number of bits. Okay, so this is what we call one's complement addition. So we have here, we can make the job of the receiver easier if we send the complement of the sum of the checksum. Okay, so um, in one's complement arithmetic, the if just a review, okay, so the complement of a number is found by completing all bits. Okay, so when we say complementing, we're complementing all bits. That means we're changing all ones to zeros and all zeros to ones. So that is what we mean by complementing it. Okay, so in one's complement arithmetic, this is the same as subtracting the number from 2 raised to m, wherein m is the number of bits required, minus m. Okay, so also in one's complement arithmetic, there are two zeros. Okay, so we are considering two zeros, one positive and one negative, which are complements of each other. Okay, so when we say positive 0, all it has all m bits set to 0. Okay, so everything that you see is set to 0. While when we say negative 0, all uh, it means all bits are set to 1. Okay, so what do we mean by all bits set to 1? So this is the same as 2 raised to m minus 1. Okay, so that is what we mean by the positive and the negative 0. Okay, so if we add a number with its complement, we get a negative 0. Okay, so when the receiver adds all 5 numbers, including the checksum, it gets a negative 0. Okay, so the receiver can complement the result again to get a positive 0. Okay, so how do we illustrate this? So we have here an example. Okay, so the sender adds all 5 numbers in one's complement, so that is what we did earlier. So the sender adds all 5 numbers in one's complement to get the sum of 6. Okay, so the sender then complements the result to get the checksum, which is equal to 9. Okay, so as you can see, so we have here uh to get the complement. So what we do, so the sender then complements the result to get the checksum 9. So where does 9 came from? Okay, note that your 6, okay, so 6 is written as 0110. So this is the binary form for number 6. So when we get its complement, okay, so what do we do when we get the complement? We just change all zeros to ones and all ones to zeros. So therefore, this will become 1001. Okay, so 1001 in decimal. Okay, so it represents the number 9. So this represents the number 9. So therefore, 6 and 9, they are complement of each other. So we can also send a message which is equivalent to 7, 11, 12, 0, 6, and 9, wherein 9 is the complement. Okay, so when the sender so the sender sends the five data numbers together with the checksum. So if there is no corruption in the transmission, the receiver receives 7, 11, 12, 0, 6, and 9 and adds them in one's complement to get 15. Okay? So if we're going to subtract 15 minus 6, so our answer is equivalent to 9. Okay? So, or the sender complements 15 to get your 0. Okay, so this shows that the data have not been corrupted. So this is how we do the checksum. Okay, so we can simplify. So we can use this figure to show the process. Okay, so as you can see, we initialize the checksum. Okay, so the answer is 6. So we have already discussed how did we arrive to 6, and then we get the we complementary 6, and the actual checksum is 9. Okay, then we send it together with your we send it together. So at the receiver end, our calculated checksum, okay, wherein the sum in one's complement must be equivalent to 15. So always remember that 15 minus 6 will be equal to 9. Okay, so in this case, the calculated checksum is equal to 0. So if it is equal to 0, that means there is no error in the information or in the message. Okay. So we have here the internet checksum. So traditionally, the internet has used a 16-bit checksum. Okay, so the sender and the receiver follow the steps depicted in the table. So as shown in the table, so the sender or the receiver uses 5 steps. So it is shown in the table. So the message is divided into 16-bit words. So the value of the checksum word is initially set to 0. All words, including the checksum, are added using one's complement addition. The sum is complemented and becomes the checksum, and the checksum is sent together with the data. Okay? So at the receiver end, the message and the checksum are received. The message is divided into 16 bits since traditionally the internet has used a 16-bit checksum. So all words are added using one's complement addition. The sum is complemented and becomes the new checksum. So if the available checksum is 0, the message is accepted. Otherwise, it is rejected. So that is how the traditional internet. Okay, so they make use of 16-bit checksum. So in our example, we just use 4 bits for easier understanding. Okay, so this is an algorithm. So when we say an algorithm, it's a program. Okay, so it is a program that is being understood by programmers. Okay, so we use the flow diagram of the figure to show the algorithms of how to calculate the checksum. Okay, so this is a program in any language. Okay, so there are different programming language available, but by using this flow chart, by using this algorithm, they can be easily written based on its specific algorithm. Okay, so note that the first loop, so there are two loops there. Okay, so we can find two loops there. So take note that the first loop there just calculates the sum of the data units in two's complements. Okay, so the second loop wraps the extra bits created from the two's complements calculation to simulate the calculation in the one's complement. Okay, so the two's complements and the one's complements, I think you're already familiar with that in your digital electronics or logic circuits classes. Okay, so This is needed because almost all computers today do calculations in two's complements. Okay, so anyway, so that is simply one's complement plus one, I think. Okay, how about the performance? Okay, so the traditional checksum uses small numbers of bits to detect errors in message of any sizes. Okay, however, it is not as strong as the CRC, or the cyclic redundancy check, that was discussed in the previous video, in the error checking capability. Okay, so sometimes in the internet checksum, we use we just use 16, but in reality sometimes it is more of thousands of number of bits. Okay, so for example, if the value of one word is incremented and the value of another word is decremented by the same amount, so for example, we make this 7 equivalent to 8, for example, but we make this 11 equivalent to 10. Okay, so we increase your 7 and at the same time we decrease your 11. Okay, so the two errors cannot be detected. Okay, why? Because if we get the sum of this, the sum will still be the same. Okay, so the sum and the checksum remain the same. Okay, so also, if the values of several words are incremented, but the sum of the checksum do not change, again, errors will not be detected. Okay, so the reason for this is because the messages are not weighted. Okay, so we do not place weight in each numbers, or the numbers are unweighted, so we term to that as like that. Okay, so however, Fletcher and Adler, okay, so they're quite popular in data communications world. Okay, so Fletcher and Alder have proposed some weighted checksums that eliminate this type of problems. Okay, so however, the tendency in the internet, particularly in designing new protocols, is to replace the checksum with CRC, but um, it is through test or through actual works, it is said to be that CRC is um, more, what do you call this, capable compared with the checksum. But anyway, we still have to discuss this so that you have an idea regarding your checksum technique. Okay, so we have here other approaches to checksum. Okay, so from those two mentioned names a while ago, so we have the Fletcher checksum, so it was named after him, and we have the Adler checksum. Okay, so there is one a major problem with the traditional checksum calculation. Okay, so if two 16-bit items are transposed in transmission, the checksum cannot catch this error. Okay, so the reason is that the traditional checksum is not weighted. Okay, so it treats each other data item equally. Okay, so if there is a change in one and then there's already a corresponding change in the other, errors might not be detected. And the purpose of this checksum is actually to detect error. Okay, so in other words, the order of data items is immaterial to the calculation. Okay, so there are several approaches that has been used to prevent this type of problems. And some examples for that is the Fletcher checksum and the Adler checksum. So this is the flow chart or the algorithm for the Fletcher checksum. Okay, so it was devised to weight each data item in according to its position. So each position have its own weight. Okay, so there are two types of Fletcher checksum. We have an 8-bit and a 16-bit Fletcher checksum. Okay, so they make use of two algorithms, an 8-bit and a 16-bit. So in the figure, it shows the 8-bit algorithm. Okay, so in the 8-bit, okay, for 8-bit, it calculates 8-bit data items okay, and creates a 16-bit checksum. Okay, so this is calculated over octets. Okay, so we termed octets as bytes and creates a 16-bit checksum. Okay, so the calculation is done modulo 256. Okay, so it says there modulo 256, or um, that is equivalent to 2 raised to 8. So 2 raised to 8 means 256. So we use modulo 256, okay, which means the intermediate results are divided by 256 and the remainder is kept. Okay? So, as you can see from the figure, it has two accumulators. Okay? So, you have your L and you have your R. Okay? So, the L, okay? So, the L accumulator simply adds data items together while the R accumulator adds a weight to the calculation. Okay? So, the same is true with the 16-bit. So, the only difference is that a 16-bit calculates on 16-bit data items and creates a 32-bit checksum. Okay? So, this is also similar to 8-bit, but it is calculated over 16 data items, which creates 32-bit checksum. Okay? So, the calculation is done using modulo 65,536, or that is 2 raised to 16, which will give you 65,536. Okay, so that is your uh, that is the difference between a 16-bit and an 8-bit. Okay, so another type is the Adler. Another type is the Adler checksum. Okay, so in the Adler checksum, okay, so the figure shows a simple algorithm in flowchart form. Okay, so an Adler checksum is a 32-bit checksum. Okay, so somewhat this is similar to a 16-bit Fletcher with three major differences. Okay, so what are those three major differences? So it says there, number one, that calculation is done on single bytes instead of 2 bytes at a time. Okay, so number two, the modulus is a prime number. Okay, so it makes use of 65,521 instead of the 65,536 uh, using the 16-bit Fletcher. Okay, and number three difference is that L is initialized to 1 instead of 0. Okay, so it has been proven that prime modulo has a better detecting capability in some combinations of data compared to an even modulo. Okay, so this is the simple algorithm flowchart for an Adler checksum. Okay, now let us so those things, so from the previous video and up to the checksum, those are what we call error detection. Okay, so we discussed them as error detection. So the there are two types of error correction actually from our previous discussion. So the first and the most logical way to do, if we detect an error, okay, so uh, either there was an error in the message itself, or the error was lost, or the message was lost. Okay, there are the most possible or the most logical way is we just retransmit. Okay, so the first type of error correction that we have, so we have two. The first is retransmission, and the other one is the forward error correction. Okay, so however, okay, so for the first type, which is retransmission, okay, so it says there that retransmission of corrupted and lost packet is not very useful for, although this is the most logical way that we can think about. So if the error is corrupted, if the message was corrupted, if the message was lost, so the first thing to do is let's just retransmit it. So let us just send it again. Okay? So, however, this is not very useful in real-time multimedia transmission because it creates an acceptable delay in reproducing. Okay, so upon knowing at the receiver end that there is a corrupted or there is a lost message, we will still again wait for another from the sender to retransmit it again. Okay, passing through the same media. Okay, that might again suffer another loss or another error. Okay, so why not check it right away there? So why not correct it right away there? Okay, so the problem here is we need to wait. Okay, so we need to wait until the lost or corrupted packets is resent. Okay, or we have to resend it again. Okay, so however, we need to correct the error or reproduce the packet immediately. Okay, so we have another technique for that, and that is what we call the forward error correction or the FEC technique. Okay, so there are several schemes that have been designed and used in this case that we collectively call them as the forward error correction techniques. Okay, so let us discuss them one by one. So the first is the Hamming distance. Okay, so we have already discussed Hamming distance as an error detection. Okay, so we have discussed Hamming distance as an error detection, but can we use Hamming distance as an error correction? Okay, so we said that to detect S errors, so if you can still remember, so to detect S errors, the minimum. Okay, so to detect S errors, the minimum Hamming distance is equivalent to S plus 1. So this is for correction. This is for detection. So this is the minimum Hamming distance used for detection. Now, for error correction, we definitely need more distance. Okay, so to correct T errors now, so for example, granted we have already detected the error. We have detected T errors. Okay, so to correct T errors, we need to have the minimum, which is equivalent to 2T plus 1. So, it is bigger or larger compared with the detection. Okay, so if for example, if we want to correct 10 bits, okay, so we detected 10 bits and we wanted to correct that. So if we want to correct 10 bits in a packet, so we need to make the Hamming distance equivalent to 21 bits. So that is 2 times 10, that is 20 plus 1. So we need to make it 21 bits, which means that a lot of redundant bits need to be sent together with the data. So we need to send more, okay, a lot of redundant bits. Okay, so one example for that is the BCH code. So if you have your data communication subjects in the future, so you will be hearing the BCH code. So it's quite popular in data communication. So it stands for Bose, Chod, Huri, Hockenham, like that, something like that code. Okay, so in this code, if the data is 99 bits, we need to send 255 bits. Okay, so imagine there is an extra 156 bits just to correct 23 possible errors. Okay, so that is an example for the Hamming distance using the BCH code. Okay, so but most of the time we cannot afford such a redundancy, but if the system permits, so it's okay, we can make use of that. So we have lots of redundancy bits that are available once an error is detected, so we can replace that with those extra available number of bits. Okay, so aside from the Hamming distance, okay, we make use of your XOR. Okay, so using XOR, so we have been discussing XOR. We have been using XOR in our previous discussion, so we're already quite familiar with this. Okay, so it says here, this is another recommendation. Okay, so another recommendation is to use the property of the exclusive OR operation. Okay, so using XOR, if we apply the exclusive OR operation on n data items, okay, so we have those different n data items, so that is from P1 to Pn, okay, so we can create any of the data items by exclusively ORing, okay, exclusive ORing all the items, replacing the one to be created by the result of the previous operation, which is your R there. Okay, so R is the result of exclusively ORing all P1 to Pn. Okay, so this means that we can divide a packet into n chunks, okay, create the exclusive OR of all the chunks, and send n plus 1 chunks. Okay, so we're chunking or we're dividing your data there. Okay, so if any chunk is lost or corrupted, it can be created at the receiver side. Okay, so what should be the value of n? Okay, so what will be the value of n? So if n is equal to 4, for example, it means we need to send 25% extra data, okay, to be able to correct the data if only 1 out of 4 chunks is lost. Okay, so if 2, you need 50%, if 3, you need 75%, and so on. So if we are allowed only to correct 1 bit, so we need to add up, okay, or um we need to send an extra 25%, okay, to make up for for the number of chunk or the number of bits that was lost in the process. Okay, so we have another term here, which is chunk interleaving. Okay, so this is another way to achieve forward error correction in multimedia. Okay, so another way is to allow small chunks to be missing at the receiver. So actually we are more lenient. Okay, so we can allow small chunks to be missing at the receiver. Okay, so although we cannot afford to let all the chunks belonging to the same packet be missing. Okay, just one or two, for example. Okay, so what do we do in chunk interleaving from the figure? Um, you can divide, okay, so you can divide each packets into 5 chunks. So as you can see there, 5 divisions in each packet. So you can create data chunk by chunk horizontally, okay, but combine the chunks into packets vertically. Okay, so um, uh, if you can see 5, 25, 15, 10, 5, so you combine them vertically. Okay, so after that, each packet sent carries a chunk from several original packets. Okay, so each data in the packet creation, it contains all the chunks available from packets 1 to packets 5. Okay, so normally the number we however, we can afford to let one chunk be missing in each packet. Okay, so for example, in packet number 3, there was a lost packet. So at the output side, there is only one chunk lost per packet. So unlike if we do not do that, it is possible that you can lose everything in just a single packet. Okay, so normally a larger number is used. Okay, so that is just for example purposes. So if the packet is lost, we miss only one chunk in each packet, which is normally acceptable. Okay, so it is normally acceptable losing a one chunk in a multimedia communication. So we allow it. So in this type of technique, missing small chunks at the receiver is being allowed. So we don't the correction is just we accept that just a single chunk is being lost, okay, or was lost. Okay, so we have here combination. Okay, so combining Hamming distance and interleaving. So Hamming distance and interleaving can be combined. So how do you do that? First, create n-bit. First is you have to create n-bit packets that can correct p-bit errors. Okay, so n-bit packets is from the interleaving, and then the T bit errors is from the hamming distance. Okay, so then interleave M rows and send the bits column by column. Okay, so this automatically correct burst errors of up to M times T bit errors. Okay, so as you can see, we have here a an increased number of corrected errors because it is M multiplied by T. Okay, bits number of errors. Okay, and then lastly, we have here compounding high and low resolution packets. Okay, so another solution is to create duplicate of each packet. So we do each packet twice. Okay, so we duplicate each packet. With a low resolution. So one is being sent using higher resolution and the other one using a lower resolution. Okay, redundancy, and combine the redundant version with the next packet. So in this method, if the last so since we are sending two, one higher, one lower resolution, if the higher resolution was lost or corrupted, we have an alternative one but having a lower resolution. Okay? So as an example, if you're going to look at the figure, okay, we're going to look at the figure, we can create four low resolution packets out of five high resolution packets, and we send them as shown in the figure. Okay, so if a packet is lost, we can use the low resolution version from the next packet. Okay, so note that the low resolution section in the first packet is empty. Okay, so therefore you can have an alternative if something is if a message is lost during the transmission. Okay, but the problem here is we use the low resolution version of the packet if the lost packet is not the last one. Okay, because if the lost packet is the last one, we cannot really recover that specific packet. So we can recover any packets that was lost except for the last one. So it says there in this method, if the last packet is lost, it cannot be recovered anymore. Okay, because of the positioning of your low and high resolution packets as shown in the figure. Okay, so for the audio and video reproduction, does not have the same quality, of course, because we have a high and lower resolution, but the lack of quality is not recognizable most of the time. So it's okay if if we replace one low resolution for a if we replace one higher resolution for a low resolution one once in a while every time that there is lost, because usually it is not recognizable for audio and video. So it is more recognizable if it is lost or it was corrupted. Okay, so those are the different ways for forward error control. Okay, so that's it. Thank you very much. This will be our last video for this topic. Okay, so thank you for watching and have a nice day. Okay, so bye.